See this question. Consider a sphere of mass m and radius r. It is hit by a cube. At what height it should be hit so that it starts rolling? It starts rolling. See this case. Suppose this is the sphere and it's kept on the surface. It's kept on the surface. Now the question is, at what height I must hit this sphere by a cube? Cube is basically a stick with pointed edges, right? This kind of stick with pointed edges. We use it in billiards, right? So it's a stick with pointed edge. Now the question is, at what height I must hit this sphere so that it starts pure rolling? See, if I hit it below, then that's going to produce VCM in this direction and omega in this direction. In that case, at the point of contact, your VCM and omega r, they are going to add together. They will add and it will lead to heavy slipping over here. So it won't roll. If VCM and omega, if I hit it below, then VCM and omega r created will be like this. In that case, these two velocities are going to add together and there won't be a rolling. There will be heavy slipping in forward direction at this point. If I hit it along the center, then this won't create omega r, because hitting along the center is not going to create any torques. It will create only VCM. Then also rolling won't take place, because at this point there will be slipping in forward direction. So it's only possible if I hit it above the sphere. In that case, it's going to, you are going to have, it's only possible only when I hit it in above the center. I must hit above the center, say at some height. We have to find that height, right? Suppose we hit at height h. Suppose we hit at height h. The moment when we hit it, the cube is in contact with the sphere. The cube is in contact with the sphere for a fraction of seconds. In that fraction, it exerts a high impulsive force which is going to create change in momentum, mvf minus mvi. So suppose VCM created is mvcm and initial velocity is 0. So that's the impulse. This is impulse, and this is going to create an impulse f delta t. Delta is the time interval for which the Q is in contact. It's also going to create impulsive torque. It's also going to create impulsive torque fh. Right, an angular impulse created is tau dt, so fh into delta t, and that's going to produce a change in angular momentum. This angular impulse is going to produce change in angular momentum, that is I omega, right, and that is 2 by 5 mr square alpha. So we find, not alpha, omega. So we find from this equation that VCM created is f delta h upon m, and omega created is 5h delta t. So it is delta t, not delta h. Delta t, 5fh delta t upon 2mr. So if you want rolling to take place, then VCM must be equal to omega r, and in that case f delta t by r m is 5fh delta t upon 2mr. So m will cancel out, f delta t is going to cancel out, so we get h equals to 2 by 5 r. If I hit at this point, then VCM and omega r created are equal, and it will start rolling. Both. This is how we can do this question. come to the next question. Let's come to the next question. Oh, this question. Here we have a solid sphere rolling on a rough horizontal surface with a linear speed v0 and collides elastically with a fixed smooth vertical wall. Find the speed of the sphere after it has started pure rolling in backward direction. You have a, say, a solid sphere. So you can have a solid sphere like this, right? This can be a solid sphere, and it collides with a vertical wall. It collides with a vertical wall. It was rolling with velocity v0. It was rolling with velocity v0, right? v0, okay. So when it collides elastically, they have said. It collides elastically. When it undergoes elastic collision, then there'll be the kinetic energy is going to get conserved. The kinetic energy is going to get conserved. And how do you define K of a rolling sphere? Say K of a rolling sphere is K of translation and K of rotation, right? K of translation, K of rotation. Since it is elastic collision, one thing I'll say, K will get conserved. So K before collision, K after collision is going to be same. Before collision, your VCM was V0, and let's say omega is going to be V0 by R. So when it collides with a smooth wall, do you think there will be change in omega? Do you think that omega, earlier your VCM was in this direction with V0, do you think omega is going to change? For change in omega, there must act a torque. So when it collides, a normal reaction acts in this direction. This normal reaction is going to change your V0, direction of V0, direction of VCM. But does this normal reaction produce a torque? This normal reaction is not going to produce a torque. Apart from that, you have force mg and you have R. So they all are not going to create any torque. Neither there is a friction. On the wall there is no friction. The wall is smooth. When wall is smooth, you won't be having any friction also. You won't have any friction also. So torque is not created. When torque is not created, your omega is not going to change, right? Omega is not going to change. Your VCM will reverse. VCM will, now VCM, earlier VCM was towards right, now VCM will be towards left. So K is remaining conserved, Ki and Kf. So I am saying Kf is going to VCM square. So they must be equal. So this omega is remaining constant. Omega before and omega after is not going to change. So I can say safely that VCM in magnitude will also not change. It means earlier your VCM was V0 towards right. Now your VCM will be minus V0. Now your VCM will just change the direction. It won't change in magnitude because omega has not changed. K is remaining conserved. So it can happen only when VCM becomes minus V0. Minus V0 means VCM gets reversed and start moving with V0 in backward direction, right? So overall result of the rolling is going to be, say, I can draw the overall result of this rolling is your V0. This is the case just after collision, V0, and in this case you have omega naught. This is the case just after collision, So in that case, what do you find? You find that this point of contact undergoes a heavy slipping, V0, and this omega r. So you'll have a friction in this direction, friction acting in this direction. Now let me tell you something about convention of VCM and omega. See, the convention says if you take VCM in this direction as positive, take this direction of omega as positive, if you take this direction of VCM as positive, take this direction of omega as positive. If you take this direction of VCM as positive, then you take this direction of omega as positive. This is the convention you follow. So if you take this direction of VCM as positive, this direction of omega should be taken as positive. If you take this direction of VCM as positive, then this direction of omega is taken to be negative. This is like positive. So in that case, we have the option either to follow this convention or this convention. If I follow this convention, then if suppose just after collision I call it t equal to 0, then I can say VCM is minus V0 and omega is plus V0 by R. If I follow this convention, I'll say VCM is V0 and omega is minus V0 by R. So let's follow this convention, right? And I can say at t equal to 0, VCM is V0 and omega is minus V0 by R. Omega is minus V0 by R. And you have a force acting, F acting in this direction. So what this F is going to do? This F is going to produce the acceleration of F by M in backward direction. This F is going to reduce V0. This is going to reduce VCM, and it is going to even reduce V0 by R, or it is going to reduce omega in magnitude. But if I consider sine, this omega will become less and less negative. Less and less negative means if I take sine into consideration, omega is increasing. So this F is going to produce an angular acceleration, a positive angular acceleration. If this direction of VCM is positive, this direction of A is also positive, this direction of alpha is also positive. So I can say A is minus F by M, in fact, or F by M in backward direction. I should write this word, or I should write A is minus F by M if I choose this convention. And what's alpha? Alpha is torque upon moment of inertia, that is 5F by 2mr. 5F by 2mr. So if I talk about VCM is going to be V0 minus AT, that is V0 minus, or if I write, if I consider sine also, if I don't take this, I write V0 plus AT, so it becomes V0 minus F by MT, and omega is omega naught, that is V0 by R plus alpha T. So you find that omega become less and less negative, or in magnitude omega will be falling, fall to 0, and then the direction of omega will reverse. Direction of omega is going to reverse, and time will come when this omega R becomes equal to VCM. So what's that time? Can you tell me what is that time? That time will be, let's calculate it, VCM equal to omega R. So I get VCM as V0 minus F by MT and R into minus V0 by R plus alpha T, or alpha is to replace it by alpha is okay. So that will give us V0 by MT, and this is minus V0 plus 5 by 2MT, or this is 2V0, and this becomes 7F by 2MT, or time taken is 4mV0 by 7F. And in that case, the finally your VCM goes. So this is the time taken by the friction to start pure rolling, for the sphere to begin rolling. So VCM, when it starts pure rolling, VCM is this 4mV0 by 7F, that is 3V0 by 7, that is 3V0 by 7. So finally the picture will be like This is going to be 3 V naught by 7, and this is going to be 3 V naught by 7R. This is going to be the case. Okay, so that's how the rolling takes place. Thank you very much.